Download this code from codegive.com, link in the description below. OK, let's dive into the world of ANOVA, analysis of variance, post-hoc tests, specifically focusing on Fisher's least significant difference, LSD. This will be a detailed explanation, combining the theory with practical code examples, using Python with the statsmodels and scipy libraries. What is ANOVA and why do we need it? ANOVA is a statistical test used to compare the means of two or more groups. It's a powerful tool when you want to see if there's a statistically significant difference somewhere among the group means, without having to run a multitude of t-tests, which would inflate your type I error rate, the chance of falsely rejecting the null hypothesis. Asterisk null hypothesis, H0 the means of all groups are equal. Asterisk alternative hypothesis, H1 at least one group mean is different from the others. Key concepts asterisk variance asterisk ANOVA analyzes the variance within each group and between the groups. If the variance between the groups is significantly larger than the variance within the groups, it suggests that the group means are indeed different. Asterisk factors and levels asterisk factor, independent variable the categorical variable you're manipulating or grouping your data by, example type of fertilizer, teaching method, drug dosage. Asterisk levels asterisk the different categories or values of the factor, example fertilizer A, fertilizer B, fertilizer C, method 1, method 2, method 3, dosage, 0 mg, 50 mg, 100 mg. Asterisk dependent variable asterisk the continuous variable you're measuring, example crop yield, test scores, blood pressure. Asterisk assumptions of ANOVA asterisk independence asterisk the observations within each group are independent of each other. Asterisk normality asterisk the data within each group are approximately normally distributed. ANOVA is fairly robust to violations of normality if the sample sizes are large. Asterisk homogeneity of variance, homoscedasticity the variances of the groups are approximately equal. This is the most critical assumption. Violations can be addressed with transformations or alternative ANOVA methods. How ANOVA works, simplified. 1. Calculate the total sum of squares, SST measures the total variability in the data. 2. Calculate the sum of squares between groups, SSB measures the variability between the group means and the overall grand mean. This is the variability we want to explain with our factor. 3. Calculate the sum of squares within groups, SSW, or sum of squares error, SSE measures the variability within each group, the unexplained variability. This is often called the error variance. 4. Calculate degrees of freedom, df related to the number of groups and the sample size. Asterisk df, between, equals number of groups, 1. Asterisk df, within, equals total number of observations, number of groups. Asterisk df, total, equals total number of observations, 1. 5. Calculate mean squares, ms divide the sum of squares by the corresponding degrees of freedom. Asterisk msb equals ssb slash df, between. Asterisk msw equals ssw slash df, within. 6. Calculate the f statistic asterisk the test statistic for ANOVA. Asterisk f equals msb slash msw. 7. Determine the p-value asterisk the probability of observing an f statistic as extreme as, or more extreme than, the one calculated, assuming the null hypothesis is true. 8. Decision asterisk. Asterisk if p-value alpha, significance level, typically 0.05, reject the null hypothesis. This means there's a statistically significant difference somewhere among the group means. Asterisk if p-value equals alpha, fail to reject the null hypothesis. This means there's not enough evidence to conclude that the group means are different. The problem with just stopping at ANOVA, where post-hoc tests come in. ANOVA tells you that at least one group is different, but it doesn't tell you which groups are different from each other. If you have more than two groups, you need post-hoc tests to perform pairwise comparisons and determine which specific groups differ significantly. Why not just run a bunch of t-tests? Running multiple t-tests to compare all possible pairs of groups inflates the type I error rate, the probability of falsely rejecting the null hypothesis. The more comparisons you make, the higher the chance of finding a statistically significant difference by chance alone. Post-hoc tests correct for this inflated type I error rate. Fisher's least significant difference, LSD. Fisher's LSD is one of the simplest post-hoc tests. It's a pairwise comparison test, and it's considered to be one of the least conservative post-hoc tests. This means that it is more likely to find a significant difference between groups than other post-hoc tests. Because of this, it is often used as a starting point for further analysis or as an exploratory tool. How Fisher's LSD works *. 1. Perform ANOVA first *. The LSD test is only valid if the overall ANOVA is significant. If the ANOVA isn't significant, there's no evidence of any differences between groups, so there's no point in doing post-hoc comparisons. 2. Calculate the LSD *. The LSD is the minimum difference between two group means required for the difference to be considered statistically significant. The formula is where *t is the critical t-value from the t-distribution with df equals degrees of freedom within groups, error df, and a significance level, alpha, usually 0.05, divided by 2, for a two-tailed test. *MSW is the mean square within groups, from the ANOVA table. *N1 is the sample size of group 1. *N2 is the sample size of group 2. 3. Compare each pair of group means * for each pair of groups, calculate the absolute difference between their means. If the absolute difference is greater than the LSD, then the difference between the means is considered statistically significant. Code example, Python with statsmodels and scipy. Explanation of the code *. 1. Import libraries *. Imports pandas for data manipulation, statsmodels for ANOVA, scipy.stats for the t-distribution, and numpy for numerical calculations. 2. Sample data * creates a pandas data frame with sample data, replace this with your actual data. The data should have a group column indicating the factor level and a value column for the dependent variable. 3. ANOVA * uses statsmodels.formula.api.ols to create a linear model. The formula value group specifies that value is the dependent variable and group is the independent variable, factor. *model.fit, fits the model to the data. *ANOVA_LM, model, performs the ANOVA and creates an ANOVA table. The ANOVA table is printed to the console. 4. Significance check *. The p-value from the ANOVA table is extracted. If the p-value is less than the significance level, alpha, usually 0.05, the code proceeds to the post-hoc test, Fisher's LSD. 5. Calculate group statistics *. df.groupb, group, value.mean, calculates the mean of the value column for each group. *df.groupb, group, value.size, calculates the sample size for each group. 6. Extract ANOVA statistics *. The relevant information, df_within, and MSW from the ANOVA table is extracted. 7. Fisher's LSD function *. Asterisk the code defines a function Fisher_LSD to perform the LSD test. This modularizes the code, making it more readable and reusable. Asterisk T critical value asterisk calculates the critical T value using stats.t.ppf. ppf is the percent point function, inverse of the CDF, of the T distribution. 1. Alpha/2 is used for a two-tailed test. Asterisk LSD calculation asterisk calculates the LSD using the formula mentioned earlier. Asterisk mean difference asterisk calculates the absolute difference between the means of the two groups being compared. Asterisk comparison asterisk compares the mean difference to the LSD. If the mean difference is greater than the LSD, the difference is considered statistically significant, and a message is printed to the console. 8 pairwise comparisons asterisk. Asterisk the code iterates through all possible pairs of groups and calls the Fisher_LSD function to perform the comparison. 9 output asterisk the code prints a message to the console indicating whether each pair of groups is significantly different based on Fisher's LSD. Important considerations asterisk. Asterisk assumptions asterisk remember that ANOVA relies on assumptions of normality and homogeneity of variance. Check these assumptions before interpreting the results. You can use tests like the Shapiro-Wilk test for normality and Levine's test or Bartlett's test for homogeneity of variance. If the assumptions are violated, you might need to transform your data or use a non-parametric alternative to ANOVA, example the Kruskal-Wallis test. Asterisk alpha level asterisk the choice of the alpha level, usually 0.05, determines the probability of a type I error. Be aware of the implications of your chosen alpha level. Asterisk interpretation asterisk even if a difference is statistically significant, it might not be practically significant. Consider the size of the effect and the context of your research. Asterisk alternative post-hoc tests asterisk Fisher's LSD is one of the least conservative post-hoc tests. Other options, such as Tukey's HSD, Bonferroni correction, Scipy's method, and Duncan's multiple range test, are available. Each has its own strengths and weaknesses in terms of controlling type I and type II error rates. Tukey's HSD is generally a good choice for pairwise comparisons when all groups are being compared, while Bonferroni is a very conservative correction that can be used in any situation where you are making multiple comparisons. Asterisk data structure asterisk the data must be in a long format, also known as tidy data, where each row represents a single observation, and you have separate columns for the group/factor and the dependent variable. Complete example with assumption checks and alternatives, incorporating Levine's test. Key improvements in the complete example asterisk. Asterisk assumption checks asterisk includes Shapiro-Wilk tests for normality within each group and Levine's test for homogeneity of variance. The p-values from these tests should be examined before interpreting the ANOVA results. If the assumptions are significantly violated, you should consider data transformations or non-parametric alternatives. Asterisk alternative post-hoc. Tukey's HSD shows how to perform Tukey's HSD post-hoc test using the scicit post-hocs library. Tukey's HSD is generally considered a more robust post-hoc test than Fisher's LSD, especially when all pairwise comparisons are of interest. Scicit post-hocs needs to be installed. Pip install scicit post-hocs. Asterisk clarity asterisk enhanced comments and organization to make the code more understandable. In summary, ANOVA is a valuable tool for comparing group means, but post-hoc tests are essential for pinpointing which groups differ significantly. Fisher's LSD is a simple option, but remember its limitations and always check the assumptions of ANOVA before drawing conclusions. Consider alternative, more conservative post-hoc tests like Tukey's HSD or Bonferroni, and use the assumption checks to guide your analysis appropriately. Remember to replace the sample data with your own.